Well, now I propose to do similar things that we did in the previous lesson, but this time, all this will be implemented in the SOP context. Let's start again with the grid. So now, to solve this grid as a cloth, we first need to create some necessary attributes and a constraint network that the solver needs to perform the cloth type of simulation, and all this can be created using the velum configure cloth node. It is also important to know that when you create velum configure cloth, in fact you are creating the velum constraint node that has cloth presets assigned. Now let's type velum and look at the nodes related to velum. So, as you can see, there are quite a lot of them, but most of them are just a preset of one generic velum constraint node. They just make it easier to configure common constraint types. That is, you can always create a velum constraint node and from here specify the type you need. See, it's generate almost all constraint types. Okay, now let's discuss what exactly the velum constraint node does. First, it creates constraint primitives, which you can hide or show using this checkbox. Now let's see why it has 3 inputs and 3 outputs. So, let's create a null and connect the first stream to it. As you can see, the first stream is just a simulation geometry, and the velum constraint has created several important point attributes on it that are required from the solver to use its points as a particles. See, before that these attributes just weren't there. Okay, now let's see what the second output gives us. So, these are constraint primitives that connect all adjacent points to each other, and as a result they stick together throughout the simulation. They also store a lot of primitive attributes, the essence of which is to describe the relationship between connected particles. It is also important to know that primitives will be constructed differently depending on the type of constraint, and also each of them has its own properties, although a lot of things are common to all types. Okay, let's get back to the cloth type and then check the third stream, which is for collision geometry, and while we have not connected any geometry to it, the output is empty. Well, after we have configured the velum type, we can send this data to the velum solver and get cloth simulation. Similar to the constraint node, it also has 3 streams. So, it takes the data that the velum constraints generates and performs dynamic simulation. Okay, now let's run the simulation and see what we get. As you can see, the cloth falls down under the influence of gravity. If you want to change the strength of gravity, you can find it in the settings of the velum solver. So, let's zero it out and play again. Since now we do not have the influence of gravity, it is stuck in place. Well, let's set the value back and move on. Now I want to add to this collision geometry, and for that I am going to use some test geometry, for example pig head. Connect it to the third input, and then lower the pig's head down so that the clothes fall on it. Good, now let's run the simulation. As you can see, the cloth is colliding with the pig's head. But since the geometry resolution is quite low, we got a terrible result. So now let's increase the rows and columns of the grid and check again. Here we go, it already looks like cloth. If you want to get a lot of detail, then you need to increase the resolution even more. But you should take into account that in this case the simulation speed will be proportionally slowed down. See, now we have a fairly detailed simulation. Okay, now I want to draw your attention to some artifacts that are due to the fact that the cloth geometry has a quadrangular topology. So, look at this, the cloth were stepwise deformed at this place, even though that the geometry has a fairly high resolution. And such artifacts are almost unavoidable, since by default the constraints are built on the basis of a triangulated version of this geometry. That is, we either need to increase the quad density decently or just triangulate it. So, let's drop down Remish node and recreates triangles instead of quads. Decrease the target size to make the triangles smaller. Then increase the smooth iteration to get an even size of triangles along with the entire geometry. Good, now let's play and see how it looks with triangles. As you can see, there are no more such artifacts, we got a very smooth result. In general, for cloth simulation it is always desirable to work with triangulated geometry. Actually, instead of these two nodes, we can create just a planar patch node, which creates an already triangulated plane. Let's set the appropriate size. Then decrease the triangle's density, since we do not need such a high resolution for further work. Okay, let's move on. Now I want to add another type of vellum to this. Since the collision geometry should be common to all, let's connect the pig head directly to the collision input of the vellum solver. Now let's create curves, and for that I will use the Draw Curve node. Choose ZX plane, then switch to the top view and start drawing. Great, let's also resample them, just to get evenly distributed points. Now let's move them up, so that they are above the cloth geometry. Like this, so now we just need to configure them as hair and send them to the solver. Well, to send the hair along with the cloth to the solver, we need to combine their outputs and then only connect to the solver. So this can be done in two ways. The first way is to merge the respective streams together and then send them to the solver respectively. That is, the cloth geometry with hair geometry, cloth constraints with hair constraints, and they will go to the corresponding inputs of the solver. That's it, this is the first way. Now let me show you the second way, and then we can check the result. Delete these nodes, then drop down the vellum pack node. This node packs vellum geometry and constraints into a single geometry. Let's duplicate it, because we need two of these. So now at the output we will need to merge only two streams instead of merging vellum geometries separately and constraints geometries separately. Then, before connecting it to the solver, you need to do exactly the opposite, that is unpack merge geometry and send it to the solver. Well, this is the second way, which is essentially the same. The only advantage is that the vellum network looks much cleaner, especially when you have several types of vellum in a single setup. So now let's run the simulation and see what we have. As you can see, they interact with each other. Okay, now I suggest adding another type of vellum to this setup. For that, let's drop down the torus. Move it up. Then adjust its properties a little. Well, now let's configure this torus as a vellum soft body. See, two vellum constraints were created at once. And on the first one, the type of cloth is set, and on the second, the type of struts. The combination of these two types creates the desired structure of constraints primitives to solve the soft body. So all we have to do now is pack it and merge with other types of vellum. That's it, the soft body added to this setup. Now let's see how it will look. There you go, they all collide with each other, but since the mass of the soft body is large, it pushes the cloth inside the collision geometry. To prevent this, let's reduce the mass. Select the first constraint, where the mass is set, and reduce it decently. Later we will definitely talk about the mass and its calculation methods. Okay, now let's check the result. As you can see, the problem has completely disappeared, no penetration occurs. Good, the last thing I want to add to this setup is grains, and for that I will use the sphere. Let's take it to the top. Then, scale it down. So, in order to generate grains and create all the necessary attributes on them for further simulation, we will use the vellum configure grains node. Connect the sphere to the first input, then check this option so that points are created from the volume. Let's also reduce the grid's size and their mass. Okay, now we just have to pack them and merge them with other types and solve. That's it, now let's check the result. As you can see, we have implemented the same thing that was done in the first lesson, but with a completely different approach. Now I want to show you how you can use dynamic nodes to control the simulation further. For this we just need to dive inside the Vellum solver. So now we are already in a dynamic context. In here, let's create a pop wind as we did in the first lesson. So, for the wind to begin to affect the simulation, you just need to connect it to the force output. Now let's add some noise to the wind and then set the direction of the wind. Okay, let's see what we get. As you can see, they are affected by the wind. In case you want the wind to affect only a certain geometry, you just need to group that geometry and specify a group for the pop wind node. So, for example, let's group the curves and make the wind affect only them. The group type must be points, let's call it hair. Good, now let's specify this group for the pop wind. Activate the group and select the hair. That's it, now let's check the result. As you can see, the wind only affects the curves. So, you can group each of them and later manipulate them separately by using the corresponding group. Now let's group the torus and make the wind affect only it. The type will be points and the name will be soft body. So let's go to the dot network and specify this group. Remove the hair, then select soft body. Good, now let's check. Here we go, the wind affects only on the torus. And finally, to cache all this, let's drop down the Vellum.io node and put it after Vellum solver. At the end you can also add the Vellum post-process node to make final adjustments to the cache geometry. So, as you can see, we completely recreated what was done in the previous lesson, but this time it was all implemented in the SOP context, which is much easier and clear. Well, that's all I wanted to show you in this lesson, so I suggest we stop here. In the following lessons, we will already start to explore all properties of the cloth constraints, since they are significant for cloth simulation, and most of these parameters are common to all other types of Vellum constraints. See you in the next lesson.